Devin accepts a dare to jump off of a 10-meter high platform at the community swimming pool. She runs straight off of the platform with a speed of 4 meters per second. How long will she be in midair? How far will she travel horizontally before she enters the water? Alright, so this will be the first projectile motion problem that we do. Or you could also call it a two-dimensional kinematics problem. So everything I've done up until this point has either involved things moving left to right or up and down. This one involves both. Okay? So here we have Devin over here on the diving board, and Devin is going to run horizontally until she gets to the edge of the board. Then when she gets to the edge of the board, she's going to fly off the board and go into the pool. We're going to attack this problem just like we've been attacking our one-dimensional kinematics problems. We're going to continue to draw our picture and put information down on our picture. We're going to write down our given. We're going to find equations. We're going to solve. You'll see that there's only one or two things that differ slightly in this problem compared to everything else we've been doing. So I'm going to start putting our information down. We know that the platform is 10 meters high. And we also know that Devin is going to run at a speed or a velocity of 4 meters per second. So that's going to be our VO. Okay? And I'm pretty sure that's all that the problem really tells us. So we're going to have to get a lot else from the problem. We're going to have to squeeze some more given out of the problem in one moment. The new step here, the important part of two-dimensional kinematics or projectile motion, is we're going to have to not only write down our given, but we're going to separate our given into x given and y given. So on the x side, we'll put down any vector that's either traveling left or right. In our y given, we'll write down any vector that's either going up or down. So for example, this VO is really VOX. In other words, this is an x piece of given because it says flat out in the problem that Devin is running horizontally. So we're going to put that under here. We're going to call that VOX. Again, we're still putting it under given. Not a lot has changed here. It's still initial velocity. It's still in meters per second. All right, well, we know something else. We know that Devin is going to go from this height to that height. So she's going to fall 10 meters. So that's a displacement. It's a displacement of negative 10. And I'm going to put that on my y side because she is going down. So I'm going to say that delta y is negative 10 meters. Again, she's going down. So we put all of our up and down given on the y side. Now that was the easy stuff because that's the stuff that actually showed up in the picture. But I think, like I said before, we can squeeze a few more pieces of given out of this problem. Once Devin leaves this diving board, she is in free fall. Gravity is the only thing acting on her, and so we know she has an acceleration. And I'm going to mark it with the y, just to remind us that this is an up and down acceleration. So she is accelerating down at negative 10 meters per second squared. All right. So now we have at least a little bit more given. I think we know something else. I think that if we know that Devin is running horizontally, and this is the tough piece of conceptual given. Devin has a horizontal velocity as she runs off of the board. She's not going to jump up. She's not going to jump down. She's going to run horizontally until she's no longer on the board. So that means that she's not running up, she's not running down. I say her initial velocity in the y direction is 0. That her initial y velocity is 0. She's not running up and she's not running down. And that's what makes this the horizontal launch problem. That's the title of this video. This is a horizontal launch. Anytime you have a horizontal launch, VOY equals 0. That's probably worth putting in your notes somewhere. So, horizontal launch problem, VOY equals 0. She doesn't launch herself up, she doesn't launch herself down. So I notice we have a whole lot of y given written down. I also noticed one thing. This will be true just about every problem in this chapter. what we're going to find is that gravity causes an acceleration in the y. I can't think of a lot that would cause an acceleration in the x. I can't think of a lot that would push Devin this way or pull Devin this way or anything horizontally. All right? I don't know. I guess maybe a bird could come flying out of nowhere and hit her while she's in midair. We're going to assume nothing like that happens. I guess wind could really blow her around. We're going to assume that the wind is negligible. So, not only this problem, but basically every problem we do, every projectile motion problem, we're going to say that the acceleration in the x is 0. There is no x acceleration unless otherwise stated in the problem. It would have to specifically say if there was an x acceleration. Now we have a lot of given to work with, and that's why I said I knew we'd have to squeeze a lot of given out of this problem, some hidden given information. And now we're going to write down our unknowns. So I'm looking at this thing, and I believe we were asked, number one, how long did it take Devin to hit the water? And number two, how far did she travel horizontally? Now, delta x, that's a vector. That's this horizontal vector. So I can put that under my x side. Time is special, and this is another extremely important part of solving a projectile motion problem, any projectile motion problem. Time is not a vector. You can't have x time and y time. It doesn't make any sense. Time just is. It has no direction. It's a scalar. So time is never going to go on the x side or the y side. Time is always going to go right here on the bottom, in the middle, all right, right on the line there. Because time is not x given and time is not y given. All right, so now we have all of our given. The next step in this problem, just like back in the old days when we were solving one-dimensional problems, is to find an equation that will allow us to use our given to find an unknown. But here's the key. You can use all of the same kinematics equations, however, your equation must use either all the y stuff or all the x stuff. You can't be mixing up x and y. You cannot, don't write this, you could not do something like vfx equals voy plus ay delta t. So you got an x, you got a y in the same problem. You can't do that. Okay? You can't have x and y given in the same equation. It's not allowed. It'll mess you up. So we want to look at our unknowns and figure out, can we use our x given to solve for an unknown, or can we use our y given to solve for an unknown? The nice little trick here is that time, because time's not a vector, you can use time in both. So time's kind of like the wild card. It's the joker. All right? You could use time with your y given. You could use time with your x given. And so this problem is very similar to a lot of problems that we will do. What we're going to do is we're going to use all this y given. We have a ton of y given. We're going to use this to find time. Then, once we find time, we can use time as a piece of x given. And so that's the great thing about time. Time is very versatile in these two-dimensional problems. We're going to use our y given, find time, then use time as a piece of x given. So I'll show you what that looks like. I see I have delta y, I see I have ay, I see I have voy, and I'm looking for delta t. So the equation that's coming to mind is delta y equals voy delta t plus 1/2 ay delta t squared. Okay? I wrote down my equation right off the formula sheet, except I made sure I used y's. All right, I didn't put delta x, and I put voy, and I put ay. So this whole thing has y given and time, and that's allowed. I can't put any x's in this equation. Now I can just solve for time. We're used to this part. Voy, that's 0. Which means this whole thing, 0 times delta t, is 0. So that whole piece goes away. We're left with 1/2 ay delta t squared. Now we're just solving for time. We're going to move our 1/2 AY over, so multiply by 2 on both sides. So the 1/2 goes away. You get 2 times delta y equals AY times delta t squared. Then we're going to move our AY over. Okay? And I'll be a little lazy there. I'll skip a half a step. And then the last thing is we're going to take the square root of everything. So you get the square root of 2 delta y over AY equals delta t. That's an equation that tends to show up a lot. It's very specific to this one problem, so we're not going to put it on an equation sheet, but that's an equation that you may want to remember or jot down and you might use again in the future. Anyway, rearranged this way, it's real simple now to solve for delta t. So we have 2 times negative 10 over negative 10. That's just a coincidence that these two were the same in this particular problem. That obviously doesn't always happen. So that gives us t, delta t is the square root of 2, which is 1.414 seconds. And that is how long Devin is in the air, which is the big part 1 of this problem. That's the main part of this problem. Next step is to find delta x. Well, like I said earlier when I gave you our little battle plan for this, we found delta t with our y given. But delta t is special. We can use delta t with the y given. We can use delta t with the x given. So now we're going to use delta t and this and solve for delta x. So I'm going to come over here. I'm going to try and save some space so I don't have to erase this. And I'm going to look for an equation with delta t and delta x and ax and VO. This same equation is coming to mind. We have delta x equals VOX delta t plus 1/2 AX delta t squared. So that formula, and again, I use the same formula, but it looks a lot different now. Because now I put all of my x given in there, my x symbols. I have delta x, I have VOX, I have AX. Again, that's one of the important pieces with this new projectile motion problem. Our equation either has y given or x given. You can use time in both. Alright, now I'm just going to start to, it's already solved for delta x, so I can plug in my numbers, and I'm already looking ahead, I'm saying AX is 0. So let me get rid of that right away. This whole piece goes to 0 then. 1/2 times 0 times t squared, 0. So now I just get delta x equals VOX times delta t. And well, luckily I know delta t from before, and I have VOX. That's a piece of given. So that's just going to be 4 times 1.414. And if you put that into your calculator, I believe you get roughly 5.6 meters. So that tells you how far Devin launched herself off of the board. She went 5.6 meters horizontally before she hit the water. That's it. That's our most basic example of a projectile motion problem. Splitting the given into x and y, and then using the same kinematics equations, but either with our x given or our y given, not both. I really hope that helped. Please let me know if it didn't. Feel free to leave a comment or shoot me an email. Thanks a bunch.